We're often taught in, early quantum mechanics that an electron can be in a state of superposition. It can be here or there or maybe both at the same time.
Right.
But how do we actually make the jump from that simple model, an electron near atom 1 or atom 2, to describing its position continuously, where it could be, well, anywhere in space?
That is a huge conceptual leap. It really is. I mean, if you've ever felt that jump from algebra to calculus, this is kind of the physics equivalent.
Mm-hmm.
So this deep dive, this is our roadmap for making that leap. We're going to unpack how those discrete probability amplitudes, those simple labels, transform into what we call the continuous wave function.
And that gets us to the really big stuff.
It gets us straight to the foundational equation of wave mechanics.
Hmm.
Our whole mission here is to turn what looks like some pretty hairy math into something that feels intuitive for you.
Okay, so let's set the stage. We have to start with that core principle, right? Superposition. Yeah. We've already established that any quantum state, let's call it CR angle vary, is just a sum of its possible base states, IR angle, and each one is weighted by a probability amplitude, which we call CR angle.
Exactly. And before those base states, the IR angle, they were just labels, atom A, atom B, something simple.
The big shift here is that we're changing the base state itself. It's no longer just a label, it's the actual coordinate position, which we can call CR angle.
That's the key. And when we use discrete labels, we're just dealing with a list of numbers, a list of coefficients of dollars. If you picture an electron hopping between atoms on a crystal lattice, its amplitude at any atom's position, say $6, is just a set of distinct points.
So what happens when we make the space between those atoms disappear?
We let that lattice spacing, let's call it a shrink. We imagine it getting smaller and smaller, heading towards zero. Now, if the physics is going to hold up, I mean, the particle has to be somewhere. That collection of discrete amplitudes, the Tekkenballer, has to become something else.
It has to become continuous.
It has to become a continuous function, a function that describes the electron's probability distribution along that entire line.
And here is where it gets so interesting, because that continuous function, which is now the amplitude for finding the particle at any position, 6 isles, that's what we call the wave function. We give it the symbol.
Yeah, it's an incredibly elegant transition.
Yeah.
The discrete amplitude due smoothly becomes the continuous function.
So this Pires is now our main tool for describing the particle's probability in space.
It is, but we have to be really, really careful about what it means.
Yeah.
Because the function is continuous, you can't really ask, what's the probability of finding the electron at exactly this $1.6?
Right, because there are infinite points. The probability would be 0.
The probability is 0. So what does it tell us? It tells us the probability density. The thing you can actually measure is the probability of finding the particle in a small but finite region around that point. Let's say a little region, delta sounds.
And that's where the famous squared value comes in.
That's it. The probability is proportional to the square of the absolute value of the wave function. The wave function itself is complex. It has a phase, but its squared magnitude is always a real positive number. That's the physical probability we can observe.
Okay, so we've got position covered with px. Now let's talk about its twin. Just as we can describe a state by its position, we can also describe it by its momentum.
Yes, using an amplitude and momentum space. We often write that as px. They're just two different but equally valid ways of looking at the very same quantum state.
And they're connected, right, through the math of waves.
Inextricably linked through something called a Fourier transform. Let's try to visualize it with a classic example. A Gaussian wave packet. So imagine a particle whose position wave function looks like a bell curve.
Okay, so its position is pretty well defined. It's centered somewhere, but it's still a bit spread out over some distance, delta 5.
Exactly. Now, if you do the math and calculate the momentum amplitude for that exact same state, you find something amazing. It is also a Gaussian distribution. It's a bell curve in momentum space.
What's the relationship between their shapes, their widths?
Ah, that's the crucial part. Let's say you squeeze the position bell curve. You make delta really narrow, which means you're very certain about where the particle is.
Okay.
The momentum bell curve does the opposite. It explodes outward. Delta P becomes enormous. Your momentum becomes incredibly uncertain.
And the reverse is true, too, I assume. If you pinpoint the momentum,
The position spreads out all over the place. Large delta L curves. You can't win.
this is starting to sound very familiar. This isn't just some quirky mathematical trade-off.
No, it's much more profound. This is the mathematical statement of the Heisenberg uncertainty principle. The product of those uncertainties, delta times delta P, has to be greater than or equal to a fundamental constant related to delta bar.
And it's not because our measuring tools are bad.
Not at all. It's built into the very fabric of reality, because a quantum particle is fundamentally described as a wave. A wave that's localized in one spot is, by definition, made up of a huge range of different wavelengths. And wavelength is momentum.
That brings us to a bit of a mathematical headache, though. How do we properly handle these continuous functions, normalize them?
Right. With discrete states, it was easy. We had the Kronecker delta. It's 1 if the labels are the same, 0 otherwise. It worked perfectly for sums.
But for continuous points, that idea breaks down.
It breaks down completely. We need a continuous version of that, and the tool we use is the Dirac delta function, delta dollar.
So what is that?
It's a bit of a brilliant mathematical fiction.
Yeah.
We describe it as a function that's 0 everywhere except at the single point $6 on.
And at that one point.
At that one point, it's infinitely tall. Which sounds impossible, I know.
Yeah.
But here's the magic trick. The total area under that infinitely tall, infinitely thin spike is exactly 1.
Huh. So what's the point of it?
Its job is to act like a filter for integration. If you multiply it by another function, say xx, and integrate, it sifts through everything and just plucks out the value of the function at 0 of xx.
I see. It's a tool designed specifically to handle the weirdness of continuity.
It's what makes the math work. It gives us our normalization condition for continuous states. The expression Lagel-Langle x got $6 is what formally tells us that a state at position $6 is distinct from a state at any other position $6. It lets us go from sums to integrals without everything falling apart.
Okay, let's switch gears to dynamics. We have this amplitude that describes the particle right now. But what we really want to know is, how does it change? How does that probability cloud move and evolve over time?
To figure that out, we actually go back to our discrete model for a second, the one with the atoms on a line. We had an equation for how the amplitude at one atom, with Lee-Galler's null, changes based on the amplitudes of its immediate neighbors.
And now we do that same trick again. We take the limit where the spacing between them goes to 0.
And that's the heart of it. As that spacing h shrinks to 0, the simple differences between neighboring amplitudes mathematically transform into a second-order spatial derivative. It becomes partial by 2a, partial by 2.
So the change at a point depends on how it relates to its immediate surroundings, its curvature.
Exactly. It's like a diffusion process. And for a free particle, just floating in empty space with no forces on it, this process gives us a differential equation. It says the rate of change of the amplitude in time is proportional to the second derivative of the amplitude in position.
That's the law of motion for a free quantum particle.
That's it. And then for the grand finale, we add in the effects of external forces, electric fields, gravity, anything, by including a potential energy term, which we write as Vesi.
And that gives us the master equation.
That gives us the full three-dimensional time-dependent Schrödinger equation. This is it. This is the quantum equivalent of Newton's finite Gauntlet. It is the fundamental rule that governs how every non-relativistic quantum state evolves through time.
And this equation has a really profound consequence. It's what gives us quantized energy levels.
Yes. If we look for stable solutions, states with a definite constant energy dollar, we use what's called the time-independent form of the equation.
Let's visualize this. The classic example is a particle trapped in a potential well, like an electron stuck inside an atom. It's in a sort of energy valley it can't escape.
Right, so inside that well, where the particle's total energy is greater than the potential energy dollars, the wave function wiggles. It oscillates like a wave.
But what about outside the well? Classically, the particle can't be there.
And quantum mechanically, it's very unlikely. Outside the well, where 5 is now greater than any, though, the equation demands that the wave function can't just stop. It has to decay, and decay rapidly towards 0.
And this demand that has to decay to 0, that's the crucial constraint, isn't it?
It is everything. For the wave function to be physically realistic, or, as we say, well-behaved, it has to be continuous, have a smooth slope, and go to 0 far away. And it turns out you can only find solutions that meet all those conditions for very specific discrete values of the energy dollars.
So you can only have E dollar, E dollars, ETD2, and nothing in between.
Nothing in between. If you try to plug in any other energy value, the math breaks. The wave function either becomes discontinuous or it blows up to infinity, which is physically impossible.
So let's just step back and look at the big picture here. What does this really mean?
It means that the fact that energy is quantized, the reason an electron in an atom can only have specific energy levels, isn't some strange ad hoc rule we made up. It's a direct mathematical consequence of the particle being a wave that is confined in space. The boundaries force the energy to be discrete.
So, to recap, we've gone all the way from simple discrete states to the continuous wave function. We used that to get a handle on the uncertainty principle, and then derived the fundamental law of motion, the Schrödinger equation, which in turn naturally explains why energy comes in discrete packets.
And the elegance of it is just beautiful.
Yeah.
The whole idea starts with a simple model of electrons hopping between atoms, and that logic just scales up perfectly to give us the single equation that governs basically all non-relativistic quantum mechanics.
A final thought for you to mull over. How does this strict mathematical requirement, this need for well-behaved wave functions that define only certain energy levels, directly relate to the specific stable size of the atoms that make up our entire world?